So what we're going to do is we're going to look at what's called a reaction mechanism. And a reaction mechanism is a series of steps by which a reaction takes place. So let's take a look at the reaction below. What this reaction below suggests is that 4 particles of AB and 1 particle of C2 will all combine at the same time with sufficient energy and correct orientation. Now the probability of this occurring is really low because it all have to have perfect orientation and enough energy for the collision. So rather what will happen is rather than all 5 reaction particles colliding at once, we'll have the reaction taking place as a series of steps where it involves the collision of a fewer number of particles at a time. So for example, I might have my first step, 1 particle of AB collide with C2. And then for my second step, I'll have a particle of AB collide with the product of my first reaction. And in my third step, I'll have a particle of AB collide with a particle of my second step. And I'll have my third step occur twice. And what we can see is that if I add these all up, then things cancel and I get my overall reaction. Okay? So when we're looking at a reaction mechanisms, we have a series of terms that go with them. The first thing is an elementary step, and this is just each step in our mechanism. So this mechanism would have 3 elementary steps, where our third elementary step is just repeated. Secondly, another thing that we have is that we want to recognize that each collision is usually a collision between only 1 or 2 particles. Okay, so either it's like a decomposition or reorientation of 1 particle, or it involves 2 particles colliding. And this increases our probability of them having the correct energy and the correct orientation. So if we look at each of our elementary steps, we have 1 of A, B, 1 of C2. So that would have a molecularity of 2. And if I look at my second reaction, 1 of AB, 1 of ACCB. So then I have a molecularity of 2. And my third would also have a molecularity of 2 because it's 2 particles colliding. So we would call each of these bimolecular. Okay, a reaction may form something in one of my elementary steps that's used in a later elementary step and is not found in my overall reaction. So if we look at our reaction mechanism that we proposed, we actually have 2 reaction intermediates. Our ACCB, which is produced in my first reaction, is consumed in my second, and my ACB, which is produced in my second step, is consumed in the third reaction. And this is not found in my overall reaction, but it is produced in the reaction. So we call this an elementary or reaction intermediate. Okay, and then the final piece of terminology we have when we're talking about reaction mechanisms is what we call our rate determining step. And this is the slowest step in our mechanism. So if we had our mechanism and we said that my first step was the slowest, it would determine the rate of the overall reaction, because my first step would determine how fast this reaction intermediate is produced. Once that reaction intermediate is produced, it's going to immediately react in the second step, and then any products in the second step will immediately react in my third step. And so as a result, my rate determining step, or my slowest step, determines the overall rate of the reaction. Okay, and what I can see is anything that in my rate determining step, if I change their concentration, then it'll change the reaction. Okay? They have to either be in the rate determining step or a step before the rate determining step. And we'll take a look at a couple examples. Now, for a reaction mechanism to be valid, it has to have 3 things. Molecularity of each of my elementary steps must be 1 or 2. The elementary steps must add up to my overall reaction, and our rate determining step must agree with our rate law. And we'll talk about how this can occur. Okay. So if this was our reaction mechanism that we're proposing, if we look at our first step, first thing, all of my elementary steps have a molecularity of 2. So my first stage is agreed upon, we've already seen that it adds up to my overall reaction. So my second one is agreed upon. And now the question is, what about my for my rate determining step to agree with my rate law? And so our generic rate law, we know, is R is equal to K times the concentration of AB raised to the M, C2 raised to the N. So if I look at my rate determining step, AB occurs once and C2 occurs once. So therefore, since AB occurs once, it should have an order of 1. And since C2 occurs once, it should also have an order of 1. So if this is our rate law, then this would be a valid mechanism. So let's take a look at a second example. So here we have our rate law and a reaction mechanism for the decomposition of B2C2 into B2C plus C2. Okay, and we're proposing a two-step mechanism where our first step is the slowest. And so the first question is the reaction valid? So we have to look at our points. So if we look at the molecularity of each of my each of my elementary steps, they all have a molecularity of 2. So it's valid. If we look, we can see that it adds up to my overall reaction. So my second step is valid. And now the question is, does it agree with the rate law? Well, if I go to my slowest step, since B2C2 only appears once, then it would have the order of 1. And so it agrees with the rate law. Let's say theoretically my slowest step was the second step, then since B2C2 occurs once in this step and would occur once in the step before it, it would have a rate law of 2 because it occurs once in the slow step, once in the step below it. But we know that that's not the case. Okay, so now the next question is, are there any reaction intermediates? So I'm going to change my ink color here. So reaction intermediates are things produced in one reaction, consumed in another. So we see that there are reaction intermediates. DC1 is reaction intermediate because it's produced in my first step, consumed in my second, and it's not found in my overall reaction. Our third question, are there any catalysts? Well, we can see that D- is consumed in my first reaction. It's not in my overall reaction, but it's produced again later on in my reaction mechanism. So as a result, D- is a catalyst. So catalysts are consumed in one step of the reaction mechanism, but then released in the later step. So now we have to draw our potential energy diagram for this reaction mechanism. Okay, so we have our information. So we know that when we start off a potential energy diagram, we place our reactants on one point and we write what they are. Now, since this is an exothermic reaction, we know that our products will have lower potential energy than our reactants, so we can add it. We can label the difference between them as the energy that's released. Now we know that for the reverse reaction, my enthalpy will be the same magnitude, except rather than being a negative, it'll be a positive because it would be required, because it's the amount of energy to go from my starting point to my finishing point. We can add our curve, and I exaggerated the curve just so that I could show some stuff in here so that we can see what's going on. Okay, and once we add our curve, we can add our activation energy for our forward reaction. We know that it's the energy required to go from our starting point to the peak of our potential energy diagram. Okay, we can show the activation energy for our reverse reaction. It's from their starting point to the peak of the potential energy diagram. Okay, and we can also show the impact of a catalyst. We know that because the catalyst provides an alternative reaction pathway with an alternative EA, We can add that, and we could even show our EA for our catalyst if we had it. And finally, we could also show our reaction mechanism on it. This is a two-step mechanism. So therefore, when I draw my curve, I'm going to have two bumps, one bump for each elementary step. And then we also know because my slowest step is my first step, it should have the highest peak. And so we can show that. So here I'm showing my two-step mechanism. It's two elementary steps. So I have two bumps. My first step is my slowest step, so it's going to have the highest peak. My second step is a faster step, so it's not going to go as high. Also, what I could do here in the valley, this is where I would expect to find my reaction intermediates. So in this case, the reaction intermediate that what I would expect to find here is DC minus.